Durgesh for inviting me. So today's talk has two parts. In the first part, I will speak about some recent results in convex hulls of random point sets. And this is more or less a survey in the first half, whereas in the second part, I will focus a little bit more on proof techniques and some of the main ideas going into our approach. Most of this talk is based on joint work with Pierre Calka. So let's begin. The convex hull of a planar point set is just the smallest convex polygon containing these points. This idea of taking the convex hull goes back to Newton, who looked at the so-called lower convex hull of a planar point set. But it wasn't really until 1864 that Sylvester got the study initiated in a more serious way, and he asked the following question: place points uniformly at random inside an ellipse. How many vertices are there in the convex hull? So if you put 4 points uniformly at random inside an ellipse, how many vertices does the convex hull have? So if you put down 3 points in an ellipse, the 3 points look like this. Now, the fourth point can be either inside or outside the triangle formed by the first 3 points. And if the fourth point is inside the triangle formed by the first 3 points, then the convex hull obviously has 3 vertices. Otherwise, there are potentially 4 vertices. And in this picture here, we see that the fourth point is outside the triangle formed by the first 3, and therefore there are 4 vertices in the convex hull of a 4-point set. It could have happened that the fourth point would be, for example, right here, which would form the convex hull would be a triangle, and this point here would no longer be an extreme point. The point that I'm trying to illustrate here with this very simple toy diagram is that we see here, even when we put down just 3, or when we put down 4 points in an ellipse, it's unclear whether there would be 3 or 4 vertices in the convex hull, but more importantly, the spatial dependencies of the points are presenting some technical obstacles, and these obstacles really lie at the heart of the problem of understanding the behavior of convex hulls, and it's a recurring theme in our subject. Let's now put down 4 points uniformly at random in a triangle. So again, the number of vertices in the convex hull is either 3 or 4. And what is the expected number of vertices in the convex hull of a 4-point set? It turns out that Sylvester, as was shown by Sylvester, the expected number of vertices in the convex hull of a 4-point set is 11/3. It's a number between 3 and 4, which is what we would expect. And I'll just point out here that the answer here does not depend upon the size or shape of this triangle. In other words, the answer is invariant under a change of scale, and it's also invariant under an affine transformation. But let's go to the general setup where we have now n points put down uniformly at random in some compact planar set. Let's always denote by Kn the convex hull point set. So by this we mean the smallest convex polygon containing the points. Said differently, the convex hull is just the intersection of half spaces containing the n-point set. Here we have a depiction of the convex hull of uniform points put down in the unit disk. The red points are the vertices of the convex hull, and the blue points are the interior points. one important statistic for the convex hull is the number of vertices, and that we denote by F0. So F0 of Kn in this talk always denotes the number of vertices in the convex hull. Okay, let's look at a couple more examples. If the mother body hosting the n points is the triangle, as we just saw, the expected number of vertices in a 4-point set put down uniformly at random in the triangle is 11/3. If the body K, on the other hand, is the unit disk, and you put 4 points uniformly at random in the unit disk, the expected number of vertices in the convex hull, again, is a number between 3 and 4, and it works out to be this rather complicated fraction, as shown by Woolhouse. I'll just point out here that this formula, this last formula, is invariant under a change of scale. Okay, one more example. Suppose the mother body is a rectangle in the plane. Put down 4 points uniformly at random in a rectangle, and ask for the expected number of vertices in the convex hull. And again, the number should be between 3 and 4, as is this ratio here. And again, I'll point out that this formula does not depend upon the aspect ratio of the rectangle. The rectangle could be a square, it could be a rectangle that's very, very narrow. It does not change the answer. Much research has gone into understanding the expected number of vertices in the convex hull of a planar set and even a high dimensional set. I just mentioned a few names here. What about dimensions larger than 2? So again, let's take K to be a compact convex subset of Rd, and we consider n IID uniform points put down in this mother body K, and Kn is the convex hull of the n-point set. It's the smallest convex polytope containing the points. If K is the unit cube, and if we put down 4 points in the unit cube, then the 4 points with probability 1 are already in convex position, and the number of vertices in the convex hull is with probability 1 equal to 4. So the only interesting number of points is when the number of points is at least 5. So let's start with putting 5 points uniformly at random in the cube and ask for the expected number of vertices in the convex hull. And you get the following answer. It's pretty clear that these formulas are becoming more complicated as the number of points in the sample increases and as the dimension increases. As one last example, let's consider a tetrahedron, and let's look at the convex hull of an n-point set where the points are put down uniformly at random in the tetrahedron. And this time we'll ask for the expected volume of the convex hull. It turns out that the expected volume is in some sense equivalent, as we'll see in a few seconds, it's equivalent to understanding expected number of vertices in the convex hull. Okay. You may try to guess the answer for the expected volume, but you probably would not have guessed this answer. Here is a formula for the expected volume of the convex hull of n random points put down uniformly at random in a tetrahedron. And the point of this transparency, hopefully it's not to lose you early in the talk, it's just to show that the formulas are becoming quite complicated and messy as the dimension increases and the number of points increases. All right, so let's go back to statistics of random polytopes. By F0, we mean the number of vertices of the random polytope. And in general, one can ask for the number of K faces of the polytope. So by a 0 face, we mean, of course, a vertex. By a 1 face, we mean an edge. And by a d-1 dimensional face, we mean a facet, a d-1 dimensional facet of the polytope. I mentioned on the previous transparency that understanding the volume of the convex hull is equivalent to understanding the expected number of vertices, and that's because of this formula due to Efron. In other words, the average vertex count gives information about average volumes. Efron's result is a cute little result and has a simple explanation. And here is the easy proof of Efron's result. So here we're relating the expected vertex count to the expected volume. And the proof is just a couple of lines. We start by writing the number of vertices, F0, of the convex hull as a sum of indicator functions. So it's the indicator that the kth point in the sample is not belonging to the convex hull of the remaining n-1 points. So this is a way of just counting when a point is a vertex or not. This is 1 or 0. It's 1 if xk is a vertex of the convex hull of Kn and 0 otherwise. And now we take expectations. These random variables on the right-hand side are identically distributed. They all have the same probability, so it suffices to look at the probability that xn is not in the convex hull of the first n-1 points. And that's this expression here. We multiply by n. Take the conditional expectation, and we come to this line here. So we condition upon the positions of the first n-1 points, and we ask for the probability that the nth point is not in the convex hull of the first n-1 points. And the probability that xn is not in the convex hull of the first n-1 points is, of course, just the ratio of the expected volume of the convex hull of the first n-1 points. That's this term here, divided by the volume of the body hosting the points. And there is the result. Here is Efron's result, a simple proof. Okay, so convex hulls have connections with many other fields. In computational geometry, they are important for approximating convex sets by random polytopes. So to understand a convex set, you may put down points I, D uniformly in this convex set and approximate the convex set by the convex hull of the points put down inside it. In optimization, the vertices of the convex hull are just the extreme points of some multivariate random samples. In statistics, convex hulls are used to understand the data depth of points. This comes about through the notion of convex hull peeling. In the study of animal behavior, otherwise known as ethology, one can try to understand the home range or the breeding territory of animals, and this is done oftentimes by looking at the convex hull of the sites where the animals are observed. Okay, just to complete this introduction, there are some very simple or seemingly innocuous questions that one can ask, but there are some surprising answers. So let's just recall that F0 is the number of vertices of the convex hull of n points put down uniformly at random in K. one can imagine, one could anticipate and think that the expected vertex count should be monotone in the input size. In other words, one could expect that increasing the sample of points should, on the average, increase the number of vertices of the convex hull. And surprisingly, there are only partial results in this direction. There are no general theorems. If K is planar, the answer is positive. There are a few other partial results that I will not mention. A second question is, if you have two sets K and L, K a subset of L, you might expect that the volume of the convex hull of n points put down uniformly at random inside the smaller set should be less than the expected volume of n points, of the convex hull of n points put down uniformly at random in the larger set. So you might expect this inequality to hold, but in fact, it does not in general. So understanding the behavior of convex hulls has some tricky inequalities, and it's quite difficult to formulate general principles related to monotonicity or monotonicity in volumes or vertex counts. All of this is to now try to show you and try to convince you that it's difficult to derive explicit formulas for statistics of convex hulls on a finite number of IID points. The formulas are quite messy and quite complicated, and there are no guiding principles like monotonicity. So instead, the investigation has focused on the behavior of statistics of convex hulls as the input increases. And it turns out that the geometry of the mother body K, in particular the shape of its boundary, determines the magnitude of growth for the expected vertex count. Here is a simulation. We have 50 points put down uniformly at random in the unit ball. The red points are vertices. Here's 50 points put down uniformly at random in the unit square. There are a few long edges. Maybe not very helpful to see only 50 points. Let's increase to 100 points. Here we have 100 points put down uniformly at random in the unit ball. Notice that whether a point is a vertex of the convex hull depends upon the locations of other points. And this is quite transparent. It's quite obvious. But I need to emphasize this point since it forms some very difficult technical obstacles when understanding statistics of convex hulls. Look, for example, at this point here. It's a vertex. But imagine that the 101st point in the sample, so we add one more point to the sample, and suppose that one extra point just happens to lie here, for example. If it lies right here, then this point no longer is a point in the convex hull. There would be an edge joining this point to that one and to that one. Here's the convex hull of 100 ID uniform points in the square. Again, there are spatial dependencies here that are quite clear. Imagine that there would be the 101st point close to this lower left-hand corner. If that were the case, then this point and this point, these two red points here, would no longer be vertices of the convex hull. Instead, there would be a long edge between the point near this lower left corner and this point here, and another long edge between this 101st point and that point there. So here we've come to 500 points in the unit ball, and again, 500 points in the unit square. All right, Okay, what can we say about asymptotics as the number of points increases to infinity? So Renyi and Solanki showed in 1963 in their seminal work that if one has IID points put down in the unit ball, then the expected vertex count for the convex hull of n of these n points displays cube root asymptotics, namely the limit of the ratio of the expected vertex count to n to the 1/3 converges to some finite positive constant c. Now, why are there these unusual cube root asymptotics? And I will give some heuristic explanation, which can be made rigorous, but here is the idea. Let's understand that a cap of the unit disk is the intersection of a half plane with the unit disk. And it turns out, and it's not too hard to believe, that every extreme point, every vertex of a convex hull is contained in a cap which does not contain any other sample point. And if there were no such cap, then this would contradict the definition of a convex hull being the intersection of half spaces containing the points. So every extreme point can be isolated or contained in a cap which does not contain another sample point. And the picture looks something like this. This cap here's a point in the sample, and this point here is contained in a cap. And I claim that this cap has area roughly equal to 1/n, with n being the number of sample points. And this is because if you have n points in a planar area in a planar region of area 1, then every point should more or less be contained in a cell of area 1/n, and that cell would not contain any other sample point. So this is just on the level of heuristics, of course, but we can expect that we should be able to find a cap of area 1/n that does not contain other points. This cap having area 1/n means that the radius of the cap should be on the order of n to the minus 1/3, whereas the height would be of order n to the minus 2/3. And that's because near the South Pole here, the graph of the circle looks like y equals x squared over 2. So the behavior of the circle is parabolic, which explains why we would need a radius of n to the minus 1/3 and a height of n to the minus 2/3 in order to come up with an area of 1/n. Well, this is to say that the expected number of extreme points should just equal more or less the expected number of points in an annulus of width n to the minus 2/3. So this cap has a width of, or a height of n to the minus 2/3. All extreme points should be located in an annulus of width n to the minus 2/3. And since there are n points, altogether, the expected number behaves like the product of n and n to the minus 2/3. Those are the heuristics. They can be made rigorous. But this explains the cube root asymptotic effect. Now, for more general planar bodies, K, having a smooth boundary, one still, of course, has cube root asymptotics, but now the limiting constant is the product of one universal constant c and the integral of the curvature to the power 1/3. So if one goes back to the previous transparency, one would, and looks at smooth bodies, one would observe that the height of the cap should behave like the curvature to the 1/3 times n to the minus 2/3. So if one did the analysis a little bit more carefully, one would pick up a curvature term, and integrating this curvature over the boundary gives this integral here. So what about mother bodies which are smooth and those which are polytopes? 15 years ago, Matthias Reitzner showed that if one starts with a mother body whose boundary is of class C2, then the expected number of vertices, or even an expected number of K faces in the convex hull scales like a power of n to the d minus 1 over d plus 1. And in the limit converges to the product of two constants. One of them is a universal constant that depends upon the dimension, and K. Remember, K is, when K is 0, we have the expected number of vertices. When K is 1, it's the expected number of edges, and so forth. So one constant is CdK, and the second constant is the integral of the Gaussian curvature to the power 1 over d plus 1. So we integrate the Gaussian curvature over the boundary, and this forms the second constant. This constant here, this integral, is known as the affine surface area, and it's invariant under affine transformations, which is what one would expect anyway, because we know that the K-phase functional should be invariant under affine transformations. Okay, so this is the affine surface area. In the case that the mother body K is a convex polytope, for example, the cube, with n vertices, then the expected K-phase functional of the convex hull scales like not a power of n, but a power of log n. So it's log n to the dimension d minus 1. And the limit converges to the product of two constants. One of them is the number of vertices of the polytope, and the second constant depends upon the dimension and K. All right, so moving along to the convex hull of IID standard normal random variables, the expected vertex count scales like a power of log n, or it's log n to the power d minus 1 over 2. This log n to the power d minus 1 over 2 more or less is the expected number of outliers in a Gaussian sample in RD. Okay, so we've looked at expectation asymptotics, and now one can ask, what are the precise variance asymptotics? And as is the case with expectations, the correct scaling depends upon the geometry. For example, if the boundary of K is of class C3, then the variance of the convex hull of an n-point set scales like n to the d minus 1 over d plus 1. And it converges, it has the same limit as one had in expectation asymptotics. The only difference is the coefficient of the affine surface area. So the variance asymptotics scale in the same way as expectation asymptotics. Same thing happens if you have a simple polytope with n vertices. The variance asymptotics scale have the same scaling as with expectation asymptotics. Here, nu kd is a constant depending upon k and d. And likewise, if one has a Gaussian polytope, the variance asymptotics of the convex hull of a n-point Gaussian set exhibit also the same scaling. These are results collected with and proved with Thomas Schreiber and Pierre Calka in the last several years. I will, in the second part of the talk, give some ideas how to prove these results. Okay, In this third part of the talk, I'd like to speak about fluctuations of convex hull boundaries. So in the last part, we dealt with expectation and variance asymptotics. And now let's try to understand the fluctuations of the convex hull boundary. So Kn is the convex hull of n IID uniform points in the unit ball. And we're going to blow up this picture by a factor of n. So n times k of n. We blow everything up by a factor of n. Maybe before going into this, I should pause and see if there are any questions.
There are no questions in the chat. If anyone wants to ask a question, please raise hand and unmute yourself.
Okay.
Maybe Joe, I have a question. So I think, so the expectation for smooth is you need only C2, but variance you need C3. Is that correct?
That's what you read the screen correctly. Whether this C3 assumption is absolutely necessary is unclear. Probably one could get by with C2 for the variance asymptotics.
Okay.
Thank
Thanks.
you. Okay, so here we're taking the convex hull and we're going to blow everything up by a factor of n. And this now gives us a random interface denoted by this notation here. As n increases, two things happen. The interface is scaling and blowing up, but at the same time, we're adding new points. So these new points create new faces, and the new faces presumably will subsume existing faces. The fluctuations of these interfaces are of interest. By the maximal radial fluctuation, we mean the width of the minimal annulus, which contains the boundary of the convex hull. We mean the width of the minimal annulus, which contains the random interface. It's a measure of maximal local roughness. And secondly, we can speak about the maximal longitudinal fluctuation. This is the maximal diameter of the faces in this random interface. So these two quantities measure fluctuations. They're the usual quantities one looks at in interfaces. So much is known concerning the fluctuations of several interfaces. For a planar object or planar system of linear scale n, there is known or believed to be a roughness of order n to the 1/3. In other words, the radial fluctuations are of this order, meaning that the width of the minimal annulus containing this boundary should be of the order n to the 1/3. And the longitudinal correlation length is of order n to the 2/3. And this can be interpreted, by the way, as the typical length of an edge in the convex hull of the extreme points in this planar object. In these situations, this planar system is said to exhibit 1/3, 2/3 scaling. Models exhibiting this scaling are ubiquitous. Some of you have seen the corner growth model. This is one example. If you haven't seen the corner growth model, I won't be able to explain it right now. The convex hull boundary is another example which exhibits this scaling, and I'll get into this in 1 second. So let's define the maximal radial fluctuation of this expanding convex hull. We're going to call it MRF for maximal radial fluctuation. And it's just to recall, it's the width of the minimal annulus containing the boundary of this expanding convex hull. Whereas the maximal longitudinal fluctuation, which we abbreviate as MLF, this is the maximal diameter of the faces in the boundary. And in dimension 2, we may obtain the growth of these fluctuations up to logarithmic precision, namely the maximal radial fluctuation scales like n to the 1/3, log n to the power 2/3. This theta of 1 means that this quantity is upper and lower bounded by a positive finite constant, almost surely. And likewise, the maximal longitudinal fluctuation exhibits growth of n to the 2/3 with a log n to the 1/3 correction term. In other words, this convex hull boundary exhibits the 1/3, 2/3 scaling. Is this a coincidence? Is there something else happening? This is maybe not quite clear yet. Let me mention that in higher dimensions, we also obtain the order of growth of the fluctuations up to logarithmic precision. But so in higher dimensions, the maximal radial fluctuation scales like n to the power chi of d, where chi of d is d minus 1 over d plus 1, with a log correction term. The maximal longitudinal fluctuation scales like n to the psi of d, where psi of d is d over d plus 1. These relations here are corollaries of a more precise result, which we'll speak about in a second. But first, let me go to another model, which maybe some of you have seen before. This is here another model where one observes similar fluctuations. Let's consider Brownian motion with parabolic drift. So the drift term is x squared over t. T here is not supposed to be time, it's just some fixed parameter. How does the Brownian motion with parabolic drift fluctuate with respect to its convex hull? Let's draw a picture. I'm actually taking a picture from another source, Hammond, and here we have the picture of what's happening. We have Brownian motion with parabolic drift. That's this jagged gray curve here. And then we take the convex hull of this Brownian motion with parabolic drift. That's the heavy dark line here. And we ask for the fluctuations of the Brownian motion with respect to its convex hull. And the facet length, or the length of the edge of the convex hull, which we're calling L, this facet length can be identified as the horizontal scale above which the parabolic curvature is dominant and below which the Brownian fluctuation dominates. That means that if one uses this heuristic, then we can find the scale of L by equating these two effects, namely the Brownian fluctuation over an interval of length L should look like L to the 1/2, whereas the parabolic curvature would be L squared over T. Equating these gives that L is behaving like T to the 2/3. But if L is T to the 2/3, then the facet length, so the facet length scales like T to the 2/3, and therefore the inward deviation of the Brownian motion should be the square root of this, namely T to the 1/3. So here we have fluctuations of Brownian motion with respect to the convex hull, which exhibit the 1/3, 2/3 scaling. And well, this reminds us of the 4 characteristics of the KPZ universality class. Namely, 4 characteristics are that there is an exponent of 2/3 on the spatial scale, an exponent of 1/3 for the scale of height. The interfaces of this motion should be locally Brownian, and that's the case in this example. And there should be some parabolic constraints, and that's exactly what's happening in this toy model. So this Brownian model that I just described has these characteristics. And the boundary of the convex hull of an IID sample appears to have only 3 of these characteristics, namely these first 2, and the last and the 4th one. The parabolic constraint for the boundary of the convex hull of an IID sample comes about because we're constrained by the sphere holding the points. All right. So just recalling the notation, the maximal radial fluctuation of the scaled convex hull is the width of the minimal annulus, and the maximal longitudinal fluctuation is the maximal diameter of the faces. And as I just said, the growth of these fluctuations are a corollary to a more precise growth result. And that's the following. So recall that if you have IID random variables, the maximum denoted by MN could have a limit distribution, which is a Gumbel distribution. Namely, it could have the distribution seen on the right-hand side. So it's difficult to obtain the distribution of the maximum of random variables that are dependent, especially those having spatial correlations. The diameters of the faces of the convex hull are spatially correlated. I mean, the faces themselves are spatially correlated, so of course the diameters are. And so are the radial distances between each face and the boundary of the convex hull. So if you take each face of the convex hull and look at the distance to the boundary, this gives us a collection of random variables, and these random variables, which are measuring radial distances, have and exhibit spatial correlations. Nonetheless, it turns out that the maximum of these radial distances satisfies a Gumbel distribution, and so does the maximum of the diameters of the faces. And that's what the next result says. The maximal radial fluctuation of this expanding convex hull satisfies a Gumbel extreme value result, namely, after scaling the maximal radial fluctuation by the right power of n, and centering around a logarithmic term and a log-log term, one gets convergence to a Gumbel distribution. And the maximal diameter of the faces also satisfies a Gumbel extreme value result, but with a different scaling. And using these Gumbel extreme value results, one can deduce as a corollary the expectation of the maximal radial fluctuation and show that it exhibits this logarithmic correction term that we saw back here. So these results are corollaries of the Gumbel extreme value result. Okay, this concludes the introduction and the first part of the talk, in which where I've tried to survey recent results in convex hull in the statistics of convex hulls. And in the second part of the talk, when we come back, I will discuss some of the proof ideas and also discuss scaling limits of the boundary of the convex hull of IID points. Okay, I think I'll stop there. Thank you.
Okay, so maybe we can take some questions if there are any. I have one basic question. You mentioned 4 properties that the KPZ interface has. And the one that is not shared here. So did you explain that it is not known, the Brownian fluctuation? Or so there's one of them was the Brownian fluctuation of the interface, right?
Right. And so the Brownian model that we discussed exhibits these 4 characteristics. And your question is related to the boundary of the convex hull, correct?
Is the third? Yes. Is it known to be not the case? Or?
Well, it's, I think, unclear. It's really unknown whether the interfaces are locally Brownian. Maybe there's a rescaling that would show the interfaces have some hidden Brownian behavior to it, but it's not apparent right now.
I see.
I mean,
Okay.
If one, I mean, this brings us to an interesting point, though, that if you consider the volume between the boundary of the convex hull and the sphere, this volume exhibits Brownian fluctuations. We will see this in the second part of the talk. So the volume, the defect volume between the interface and the sphere exhibits Brownian fluctuations. It converges to a Brownian sheet, actually. But that's different than saying that the interfaces themselves exhibit Brownian motion.
Okay.
I would like to ask a question, Joe, if I may. Hi, this is Frank Den Hollander.
Hello, Frank.
Hi, great lecture. Is anything known when your points become something else, like little objects, like a square or a sphere? I'm asking for obvious reasons because then you get into all these interesting models of disk in the plane that we have been thinking about. So what is known when you give them a shape?
So you want to look at the convex hull of a collection of IID very small random sets, correct?
For instance, yes. Or deterministic sets like squares or maybe triangles or balls.
Yeah, I'm not aware of much work in this direction. On the other hand, one could suppose that the random points exhibit some noise and are located inside, because of the noise, they're located in some small region around the sample point. So the noise term creates some extra effect, and there are results which I have with Pierre, which are about to appear in the Annals of Applied Probability, which show that the rescaling one needs depends upon the noise term in a very explicit manner. But to get to your question about replacing points with small random sets, I'm not aware of much work in this direction.
Okay, thank you very much.
Yeah, you're welcome.
Any other questions?
One question, Joe. So you said this 2/3, 1/3 scaling is for planar models in KPZ class, but the exponents you get, are they sort of again believe there is some KPZ models in higher dimensions and these are the exponents, because you have exponents even in higher dimension, right?
We do, and they are consistent with what one could expect for KPZ growth in higher dimensions. That's this relation here.
Okay, thanks.
But I want to make it clear that I'm not claiming that we have KPZ growth, but there's something happening here which I don't completely understand. Maybe this is just a coincidence.
Okay, so if there are,
and it was a survey. It was a survey of some results of giving expectation and variance asymptotics. In this next part of the talk, I'd like to talk about scaling limits of the boundary of the convex hull. And as we do this, we will understand some of the proof details and some methods that we're using that are behind all of our arguments. Let's start with the simplest possible case. The simplest possible case is to consider, of course, a smooth convex body, but let's take the convex body to be the unit ball. We put down IID uniform points in the unit ball, and we already have seen this picture. 100 points in the unit ball have a convex hull that looks like this. And if we increment to 500 points, we get a convex hull looking like this. And now we can ask the following question. As the number of sample points increases, what is the scaling limit of the convex hull boundary? It's of course obvious that as the number of points increases, the convex hull fills out the unit ball, and the boundary of the convex hull approaches the unit ball. This is too simple, and we're not interested in understanding the rate of convergence of the boundary of the convex hull to the sphere. We're not interested in this, although it could be understood by our techniques, but we're interested in the following question. If we rescale the boundary in a certain way, do we get a limit object? What is the right scaling to use so that a limit object, so the boundary under rescaling converges to some limit? So what is the scaling limit? Let's understand this question by taking an IID uniform point set in the unit ball of cardinality n. This is called xn. So by xn, we always mean an IID uniform point set in the unit ball of cardinality n. Here is xn and its convex hull. Remember that in the first part of the talk, we observed that there is parabolic geometry. The sphere near the South Pole looks like x squared over 2 in dimension 2, and in higher dimension, it looks like the norm of x squared over 2. So we already observed this parabolic geometry. This means that because the geometry of the unit ball near the boundary is parabolic, not just near the South Pole, but everywhere, because of this parabolic geometry, any transformation of the unit ball into rectangular coordinates should be a transformation such that the scaling in the radial direction is the square of the scaling in the angular direction. So we want to find a transform that is parabolic in this sense. The question is, what transformation does the job? So look, given an IID point set of size n, we assert that there is a transformation, here denoted as T superscript n, that carries the unit ball into the upper half space, Rd minus 1 cross R plus, and it produces this picture. So we claim that there's a transform which carries the convex hull of an IID point set, that's this left-hand picture, into this picture on the right-hand side. This transform has the property that it takes the boundary of the convex hull, depicted in green. And by the way, we're only working in dimension, this picture is only valid for dimension 2. We have the boundary of IID points in the unit disk. The transform T, which depends upon the number of points, carries this boundary into this collection of inverted, nearly parabolic segments. So green gets sent to green. And the points in the interior of the convex hull get sent to these points in the upper half space. The transform also has the property that it carries the sphere, or the boundary of the unit ball holding these points, into this line here. So more precisely, this transform carries the boundary of the convex hull to this festoon of inverted down quasi-paraboloids. And they're quasi-paraboloids. They're not exactly parabolas, but they're parabolas in the limit as n goes to infinity. They're quasi-paraboloids because they're inverted paraboloids of the type minus x squared over 2 plus an error term going to 0 as n goes to infinity. So these down paraboloids, or quasi-down paraboloids, are maximal in the sense that this segment here, this paraboloid, is maximal in the sense that it has the maximal possible height, so that its interior does not contain any other sample points. So this interior of this down paraboloid is empty, as is this one, as is this one. And that's how one obtains this festoon of inverted down quasi-paraboloids. You take the down paraboloids and you push them up into the sample in the maximal possible sense until they are suspended on these points. And these points, where they're suspended on, are exactly the images of the vertices of the convex hull. We will say more words about this picture in the next few transparencies. But what about these up quasi-paraboloids? What about the red ones? It turns out that a point in the an extreme point in the left-hand picture is carried to this point here, and this point, which is the apex of this red parabola, has the property that it's the apex of a parabola which is not covered by the up parabolas at the other points. So every parabola is colored red if the parabola and its interior is not covered by the union of the remaining parabolas. So once again, the rule is that you look at points here in the upper half plane, and every point is the apex of a parabola, and you color the parabola red if the parabola and its epigraph, or that's to say its interior, is not covered by the union of the interiors of the remaining points. So this parabola here is not colored red because it's obviously covered by the union of the epigraphs of the remaining parabolas, whereas this point is the apex of a parabola such that its epigraph is not covered by the union of the remaining paraboloids. And that's the rule for coloring a parabola red or not. And it turns out that if you have an IID point set in unit ball of cardinality n, xn, then a point in this picture on the right-hand side is extreme if the up quasi-paraboloid with apex at that point is not covered by the union of the remaining up paraboloids. It's what I just said. This definition summarizes what I just explained. It's the rule for coloring the parabola red or not. And the basic idea here is that this transform preserves extreme points, namely extreme points in the convex hull, which are these vertices, are carried to extreme points in the right-hand picture, namely this point is an extreme point, that point's extreme. So one can characterize the extreme points using these up parabolas, and you can also characterize extreme points using the down parabolas as well. Okay, so we are just asserting that there is a transform. It depends upon the sample size, which carries this picture into the right-hand picture. In a few minutes, I will tell you what the transform actually is. So here are some properties of this transform Tn. It sends extreme points to extreme points. That's property 1. Property 2 is that Tn takes this IID sample in the unit ball to a rate 1 Poisson point process in the upper half space. So asymptotically, Tn carries uniform samples in the disk to uniform samples in the upper half space. And of course, the Poisson point process is the probabilist way of defining uniform points in an infinite region. I'm just remind you that the Poisson point process in space has the property that it puts down a Poisson, in every region it puts down a Poisson number of points, and the Poisson random variable has parameter equal to just the volume of that region if it's a rate 1 Poisson point process. And secondly, the number of points that one sees in disjoint regions are independent Poisson random variables. This characterizes the Poisson point process in the upper half space and in space in general. The main point here is that Tn takes uniform samples in the disk to uniform samples in the upper half space, asymptotically. And third, this transform takes the boundary of the convex hull into this green festoon of inverted quasi-paraboloids, and in the limit, as n goes to infinity, these quasi-paraboloids turn into actual paraboloids. So that's property 3. And these actual paraboloids are just translates of y equals minus x squared over 2 in dimension 2. And in dimension d, it's translates of y equals negative the norm of x squared over 2. And the fourth property that's not obvious at all, but it will be in a few minutes. The fourth property is that Tn, the transform Tn takes the boundary of, it takes the unit sphere, Sd minus 1, and it sends it into a subset of the hyperplane, Rd minus 1. That's this green line here. And it sends it into a subset having an area roughly equal to n to the power d minus 1 over d plus 1 up to some constant. And we will say more about this in a few minutes, but this explains why one might expect to see expectation and variance asymptotics of this order, because the number of extreme points in this picture here should be proportional to, well, here's an extreme point, there's an extreme point, there's an extreme point. The number of extreme points should be proportional to the surface area of this set here. And this surface area turns out to be of the order n to the d minus 1 over d plus 1. That's not at all clear from the picture, but it will be in a few minutes. Okay.
Joe, one interruption. There's a question. So, pardon it. So the question is whether this is all valid for any dimension, and also
yeah, this is all valid for any dimension. It's a good question. That's why I'm working in SD minus 1 here, and here's BD. So this is, the picture is a two-dimensional picture, but the properties are valid for any dimension, and in higher dimensions, we would have, in this left-hand picture, we would have the unit points inside the unit ball, and these parabolas would become paraboloids in high dimensions. So yeah, this is all valid for higher dimensions. Thank you. Okay, so there are some advantages to studying this rescaled picture. One advantage is that the spatial dependencies are often easier to localize in the rescaled picture. We'll come to this, we'll say more about this in a few minutes. And it's becomes easier to understand the space correlations. So the spatial correlations turn out to decay exponentially fast with respect to distance, meaning that the extremality status of a point, of course, depends upon nearby points, but the correlations turn out to decay exponentially fast with respect to the distance, as we'll see in a few minutes. And this leads to asymptotic independence and the central limit theorem for the number of extreme points, or more generally, the number of K faces in the convex hull. And a third advantage is that this picture makes it transparent what the scaling limit of the convex hull boundary is. It turns out to be this festoon of inverted down paraboloids. So what is the transformation that does the job? And let's start with dimension 2. Remember that we want a parabolic transformation. What we do in dimension 2 is we take a point in the disk with polar coordinates r and theta, r being the distance from the origin, 1 minus r being the distance from the boundary of the unit disk, and the distance to the boundary is scaled up by a factor of n to the 2/3. So we do a scaling in the radial direction of n to the 2/3. Because we want a parabolic transformation, one that preserves the geometry, we need to scale in the angular direction by the square root of this, namely n to the 1/3. Of course, there are other parabolic scalings besides these two. One could imagine, for example, n to the 4/3 and n to the 2/3, or n to the 10th power and n to the 5th power. We've chosen this one for a reason, and the reason is that this transform takes the unit disk and sends it to a region in the upper half plane of area roughly equal to n, the product of n to the 1/3 and n to the 2/3. So this is good because one ends up seeing in the image roughly 1 point per unit volume. There are n points altogether, n sample points altogether. They all get sent to a region having area n, so one sees roughly 1 point per unit area, which is the way it should be. So this is the transformation that does the job, it turns out, in dimension 2. And in higher dimensions, we need a way to measure angles. In particular, we need a way to maybe measure the angle that a point makes with the North Pole of the unit sphere. And for this, we can use the inverse of the exponential map. So the details are as follows. Remember that the exponential map goes as follows. Let tangent be the tangent space to the sphere at the North Pole. The exponential map maps the tangent space to the sphere at the North Pole to a vector, to a point in the sphere lying at the end of the geodesic of length norma v, where v is a point in the tangent space, starting at the North Pole and having direction v. This is a standard map used in differential geometry. And now we have a way to measure angles with respect to the North Pole. In higher dimensions, we use the following transform. We look at the distance a point has to the boundary, that's 1 minus norm of x. We rescale it by n to the 2 over d plus 1 in the radial direction. And then we take the angle that the point makes with the North Pole as measured by the inverse of the exponential map, and we scale this by the square root of n to the 2 over d plus 1. So this transform carries the disk into a region in the upper half space of volume equal to the product of n to the 2 over d plus 1 times n to the d minus 1 over d plus 1. Namely, the image of the unit ball has a volume of area proportional to n. And it carries the sphere into a subset of the hyperplane RD minus 1 having area n to the d minus 1 over d plus 1. Each of the d minus 1 components here is scaled up by factor of n to the 1 over d plus 1, giving us that the sphere maps into a region having this area roughly. Okay, so this transform turns out to do the job, and this transform does the job for the unit ball. If we started, for example, with an IID sample of points in the unit cube, one can ask, is there a transform that maps these points into a well-behaved set that's more amenable to analysis? And it turns out the answer is yes. We can find a transform which takes the points in the unit cube and sends these points in the cube to points in the upper half space. It sends the boundary of this convex hull into a limit shape, into a limit festoon that's similar but not exactly the same as the parabolic festoon. And given an IID Gaussian sample in RD having this standard normal density, there is a third transform. I'm calling it Tn, but it's not the same transform. There's a third transform which sends the Gaussian sample to points in the product space. So now it's not just an upper half space, but it's a product space. It sends the Gaussian sample to points in the product space, and the Gaussian sample or the boundary of the convex hull of our Gaussian sample is sent to a limit parabolic festoon, but this limit parabolic festoon is not suspended by rate 1 Poisson point process. Instead, it's suspended on a Poisson point process whose density is proportional to the exponentiated height with respect to the hyperplane RD minus 1. Namely, this is the density of the limiting Poisson point process under this transform Tn. So given an IID Gaussian sample with this density, we can find our transform as follows. We take all the Gaussian points and we rescale them so that nearly all of them are inside the unit ball. And the proper rescaling is to rescale by this scalar r, which depends upon n. When one rescales by this point r, then what we do is follows. We take a point in the plane with polar coordinates r and theta, and we rescale each point by Rn. This has the effect of putting most points, but not all points, inside the unit ball. We look at the difference between the distances of the rescaled points and the unit sphere. That's this 1 minus r over n. This can be positive or negative. It's usually positive. It's positive for most of the points. Then we rescale this by Rn squared, and this angle is scaled by the square root of Rn squared. And it turns out this is the proper transform, and it produces the following picture. So here's the scaling limit of the convex hull of a Gaussian sample. Again, the green festoon of inverted parabolas consists of translates of this down parabola, and it's suspended on points of a limit Poisson point process having this intensity density. The blue points here, maybe it's not visible, but this point is blue, that's blue, that's blue. These are the images of the extreme points of the Gaussian sample in the asymptotic limit as the number of Gaussian sample points goes to infinity. So that's the picture. Now let's focus on understanding the proof techniques for the K-phase functional of the convex hull of an IAD uniform sample in the unit ball. And some of the proof techniques here are, with some adaptation, can be used to understand statistics of the convex hull of IID samples in hypercubes, as well as for IAD Gaussian samples. Let's focus on understanding the simplest possible case when we have IID points in the unit ball. So let's go back to the picture that we've already seen in the unit ball. We have this transform, which takes the convex hull of an IID sample in the unit ball and sends it into this picture on the right-hand side. It takes the boundary of the convex hull to this inverted festoon. It transforms the d-1 dimensional faces of the convex hull, namely the facets of the convex hull, into subsets of these inverted quasi-down paraboloids. So in dimension 2, this edge is sent to this piece. In higher dimensions, a face is sent to a subset of the down paraboloid in this picture. The vertices of the convex hull, being the intersection of d hyperplanes of dimension d-1, are transformed by this transform Tn into the intersection of d inverted quasi-down paraboloids. Extreme points are mapped to extreme points, and k faces in the left-hand picture are mapped to k faces in the right-hand picture. So if we can understand the number of vertices or k faces in the right-hand picture, we've automatically understood the number of k faces in the left-hand picture. All right, so let's now consider any point here in the right-hand picture, extreme point or not, and to every point in the right-hand picture, we attach a score. Now, because the points in the right-hand picture involve quasi-paraboloids that depend upon n, we need to attach a score to points that reflects this dependence on n. So that's the purpose of this superscript. The score at a point in the right-hand picture, which is denoted by psi k, so you pick a k integer between 0 and d-1, and you attach a score to points here as follows. So if the point is extreme, that's to say, if it's this point or that point or that point, then the score is simply the product of 1 over k plus 1 and the number of k faces in this festoon which contain the point. And otherwise, if the point is not extreme, for example, if it's one of these points, we let the score be 0. And in this way, if we sum these scores over all points W in this point set, we simply pick up the cardinality of the K faces in this festoon. We pick up the total number of K faces in this festoon, which corresponds to the total number of K faces in the original picture. All right, so just to recapitulate, if a point is extreme, we define the score this way. If the point is not extreme, we set the score to be 0. And therefore, the number of K faces in the festoon is given by the sum of the score functions over all points W lying in this right-hand picture. So now we've expressed the number of K faces in the convex hull in terms of the number of K faces in this festoon of quasi-paraboloids. Notice that this is a sum of random variables. And the number of random variables is simply the number of points in the right-hand picture. For many of these points, these random variables are 0, and otherwise they're equal to this non-zero number. The difficulty here, and we saw this even at the beginning of the lecture, the difficulty is that these random variables are spatially correlated. Very, very spatially correlated, making their asymptotic study difficult. We claim, though, that the geometry in this right-hand picture localizes. In other words, the extremality status of a transform point in the right-hand picture is determined by local data. And by local data, we mean data in a cylindrical neighborhood of this point. And we make this rigorous as follows. So, given any point W in this upper half space and a parameter R, let's let CR of W be the cylinder of radius R through the point W. And here's the key idea. Maybe it's the key idea of one of the key ideas of this second lecture, namely, for every score, psi k, given a point W in this right-hand picture, there is a random variable R that depends upon W and all the data, xn, in this right-hand picture, such that the score at this point is completely determined by the data in this radius R cylinder around the point, meaning that if you add points A outside this cylinder, then it does not change the value of the score. So if the point W is here, the claim is that there is a cylinder around this point. So here's the point W. There's a cylinder around this point of radius R such that data outside this cylinder do not change the score. And this random variable R, which defines the radius of this local cylinder, is not just finite almost surely, but it has an exponentially decaying tail. And this is another way of saying that these scores are exponentially stabilizing. The radius of stabilization has an exponentially decaying tail. This is a non-trivial but essential observation to proving limit theorems for sums of scores. So the number of K faces, we recall, is given by this sum. This coincides with the number of K faces in the original convex hull. And we've thus represented the K phase statistic as a sum of random variables that are exponentially stabilizing. And since these random variables have spatial dependencies which are well controlled, it could happen, and it should happen, that the sum of these scores should behave like a sum of IID random variables. And this is actually what happens. There's a large literature on the limit theory for sums of stabilizing scores. And here we have an example of a stabilizing score in the context of statistics of convex hulls. So now we can bring to bear some of the theorems dealing with sums of stabilizing scores. For example, one knows that if you have a sum of stabilizing scores, then a sum of stabilizing scores exhibits a law of large numbers. And we obtain, for example, this first weak law, this first result here, namely the expectation of the k-phase functional scaled by n to the d minus 1 over d plus 1 converges to some limit constant. This scaling here is just the expected number of non-zero scores, by the way. What about variance asymptotics? So to treat variance asymptotics, we need to introduce a little more terminology. Recall that we have already defined the score function at a point W with respect to this transformed point set. It's defined exactly like this. Now, define analogously the score function psi infinity to be analogously the same score function, except now it's defined with respect to the limit Poisson point process. Namely, we replace these transformed points xn by the limiting point process p. So p is a Poisson point process of intensity 1 in the upper half plane. We have a festoon suspended on these points, and we define psi k to be 1 over k plus 1 times the cardinality of the k faces in the limiting festoon, which contain W. And that's if the point is extreme. Otherwise, we define the score function to be 0. So the point is we can define some limit score functions. With these limit score functions, we can define the following constants. So letting psi k of infinity be the limit k phase functional, let's define for points W1 and W2 in the upper half plane the covariance of scores at points W1 and W2. This is just the covariance. And then in this term, we integrate this covariance over all points having spatial coordinate at the origin and a second point of the type V2, H2. Where V2 and H2 vary over the upper half plane. So this defines sigma squared, the integral of the expectation of the score squared, where the spatial coordinate of the score is at the origin, plus this triple integral. The first question one may ask is this triple integral even, does it even exist? The answer is yes, it exists. It's finite because of asymptotic decorrelations, namely this covariance decays to 0 exponentially fast with the distance between W1 and W2. Therefore, if you integrate the covariance, you end up over the spatial coordinate, you get something finite. If you integrate over the height coordinate, you also find something finite because the scores also decay exponentially fast in height. The point is this constant sigma squared is well defined, and the variance of the k-phase functional, when properly normalized by n to the d minus 1 over d plus 1, converges in the limit to sigma squared. So this gives variance asymptotics. One can also find rates of asymptotic normality for the k-phase functional. This next result is actually due to a joint work with Raphael Lachiez-Ray, Matthias Schulte. It was published last year. The k-phase functional on the convex hull, or of the convex hull, when centered around its mean, and when scaled by the square root of the variance, converges to a limiting normal with a rate of convergence in the Kolmogorov distance given by 1 over the square root of the variance. So this rate of normal convergence is a consequence of a more general result, which gives rates of normal convergence for sums of stabilizing scores in general. We already saw in the previous transparency the order of growth for the variance. The order of growth of the variance is known, and therefore the right-hand side is of the order 1 over the square root of the variance. Okay, this rate of normal convergence is probably optimal and probably cannot be improved. All right, so what's the advantage to rescaling and using this transform Tn? If we're only interested in central limit theorems, then rescaling is probably not required. And actually, it's definitely not required in order to see that score is localized. But if you want second order results like variance asymptotics, and if you want to find scaling limits of boundaries, then this transform is necessary. Okay. Let's conclude with one last result here. We've already introduced this exponential map, and now using the exponential map, let's define the following Brownian sheet. So given any sigma squared, any parameter sigma squared, we consider the Brownian sheet with variance coefficient equal to this parameter. And this Brownian sheet is defined on the region of the exponential map where it's 1 to 1. And that's to say that we're defining a Brownian sheet that's a mean zero continuous Gaussian path process indexed by RD minus 1, having this covariance structure. So we take now 2 points, V and W, in RD minus 1. We look at the rectangles with corners V and W. One corner is the origin, the other corner is V. Likewise here. Look at the intersection, take the exponential map of this, which maps it onto the sphere, take the surface measure of this inverse image of this image, multiply by sigma squared. The notation here is possibly not the best because this is representing surface measure of a set on the unit sphere, and this is some external parameter sigma squared. So this defines a Gaussian path process, and we can show the following, that if we now consider the volume between the convex hull and that part of the sphere, or that part of the sphere which coincides with the exponential map of this rectangle, 0 to V, then this defines a volume. And this volume, when centered around its mean and properly scaled, converges to this Brownian sheet that was defined on the previous transparency. So the convergence here takes place in the space C, in the space of continuous functions on RD minus 1. The variance of Vn actually does scale this way, and the way to see this is that there are roughly n to the d minus 1 over d plus 1 facets, and each facet contributes a defect volume. So if these defect volumes were independent random variables, they're not, but if they were, we could expect that the variance should scale like the product of this many facets and the variance of each defect volume contributed by the facet, but each facet contributes a volume which is equal to the product of the facet area and the defect height. And the facet area looks like this. The defect height looks like that. If you multiply this number and this number together and square them and multiply by this, then you end up with this term. That's just a rough idea of this scaling factor in front. Okay, so this is the Brownian limit result, and well, there are some other results, but I've run out of time, so I thank you very much for your attention. Thank you.
Okay. So maybe we can take a few questions first. So are there any?
So one question, Joe, when you looked at the model on the upper half plane, the translation invariance is not the same it's translation invariant along RD minus 1. Is that correct? Not along the height direction. And this is...
You're referring to this picture?
Yeah, and the score functions also. The translation is along the coordinate V, but not H. Is that correct? Or
that's correct.
and that is somehow, you don't, that somehow leads to this, from what you explained in the beginning, it's not all of them contributing, but only some contributors also captured in the way.
Right, so in this picture here, we have points in the upper half plane. These points are the images of all of the points in the unit, all of the n sample points in the unit ball. And some of the points in the interior of the convex hull are sent to points which are far away from the half plane here.
Okay.
Whereas points near the boundary of the convex hull are sent to these points. And the actual boundary of the convex hull, which is this picture, is sent to this festoon. And as Yogesh is pointing out, in this picture we have, in the limit at least, we end up with a stationary process in the spatial direction. The sphere having, of course, it's isotropic, so one expects stationarity in the limit. Does that help with your question, Yogesh?
Yes, thanks.
So in the Gaussian case, there was on one of the slides that this, you have a stationary process. I mean, it's a Poisson process, stationary in the RD minus direction. And then you build some parabolas on that. That's how the lower envelope describes the picture. Is that, I mean, there was in one of your slides such a picture, right?
I've changed. Can you see the slide now?
Yes, this one. So did you say that in the case of the unit ball rescale, is it coming to the same one or?
So in the case of the unit ball, we end up, let me just go back. In the case of the unit ball, we end up with a limit festoon, which is suspended on Poisson points in the upper half plane or upper half space in general dimension. So in the case of IID points in the unit ball, they're all sent to via a scaling transform to points in upper half space. It's Poisson points with rate 1 in the limit. But in the case of Gaussian input, our transform sends points to this picture. Here, it sends points to Poisson points in all of space, not just in the upper half space, but they're sent to all of space. There are very few points
in the negative
with small negative height coordinate and many points with large height coordinate. That's this e to the h term here.
Yes.
So the scaling limit of the Gaussian sample gets sent to a Poisson point process that is definitely not uniform. It's not a rate 1 Poisson point process, and it favors putting points high above the horizontal axis or the horizontal plane. And it punishes putting points with very large negative coordinate.
Okay. Yes.
And then once you have this limit point process, then you do this trick of suspending parabolas on these points. These are inverted parabolas. You suspend parabolas in the maximal sense on these points, and this provides the scaling limit of the boundary of the convex hull of the Gaussian sample. Does that help you?
Yes, yes. So that answers completely. Yes. Thank you. Yes.
You're welcome.
Any other questions?
I mean, I can just point out that
yes.
this scaling transform we need one scaling transform for the points in the unit ball, another scaling transform for Gaussian sample, a third scaling transform for points that are hosted by a polytope like a cube. And if the points are not uniform in the unit ball, if they're put down with an arbitrary density, the same transform will work. And it turns out that the intensity of, or the density of the points in the unit ball, that the density of the original sample is important, but it's only the density near the boundary of the unit ball that will contribute to the asymptotics.
I see. Okay. So are there any other questions? If not, maybe all the participants can unmute.
Manju, can I ask one more question?
Yeah, go ahead, Nishan.
Yeah. It might be a bit of a naive question, but suppose one was to start with just an open set and in R2, and so we drop the assumption of convexity, and now we pick endpoints independently from this open set, and we define a random graph in the sense that we keep an edge if it is completely contained in the open set. So open connected, of course, let's assume it's connected. And now if we look at cycles in this graph and take the interior of these cycles appropriately defined, then would this have similar behavior as what you have for convex sets? Sorry, the question ran over a bit too long, but was it clear what I was trying to say?
I think it's clear. I don't think the answer is clear, though. I have not thought too much about such a question. I thought you were going to ask a slightly related question. Suppose you have IID points in the plane, for example, and they don't follow a Gaussian distribution, but some other heavy-tailed distribution. And are there results known in this direction? And actually, you can find heavy-tailed distributions where the expected number of points in the convex hull does not even grow with the sample size. But that's also another question. I haven't thought too much about the question that you posed.
Thank you.
You're welcome.